All right, this is a sample problem of RC circuits, but this is a complicated circuit now, at least because there are two capacitors in here. Since there are two capacitors, there are two time constants. So as a result, the differential equations that we are going to get for writing circuit equations will be much more complicated. So this is something that we cannot solve right now. This is too complicated for us. But we can say something about the physics of what's going on at specific times, right? The question is something like that. The initial conditions are given at time t equals 0. Both capacitors are empty. They don't have any charges. And we would like to find the currents in each branch at time t equals 0. And also we would like to see what happens in terms of the currents and the charges at time t equals infinity, right? This is the question. Right? I have chosen the values in the simple way to understand. R1, R2, and R3 are just 1, 2, and 3 ohms. The capacitance values are equal to each other. So let's discuss what happens at time t equals 0 when both capacitors are empty. And then after that, we will pass to the t equals infinity case. So at t equals 0, the essential idea in here is this: the capacitors are empty, so there are no charges on the capacitors, which means potential drops on the capacitors are equal to 0. So let's see it like this: no potential drops on caps. Let's remember that just as in the previous case, the current that goes into a capacitor continues unaffected from the other side, right? It's one of the properties that we have discussed at the beginning. There's another thing. There's no potential difference in here. So as a result, if I take that part of the circuit and replace it with a single wire, right? What I'm going to do is this: I'll just eliminate these capacitor plates and replace this with a wire. In that case too, the current that passes in here basically continues to the other side unaffected, and there's no potential difference in here. So replacing the capacitor with a wire has the same effect on the rest of the circuit as an empty capacitor in here. So as a result, if the capacitors are empty, there are no potential drops on the capacitors. So let me write it down like this: is empty capacitor, right? Empty capacitors implies no potential drops on capacitor, which implies that, right, you can replace them with wires with zero resistance, so that there won't be any potential drop on the wire, and still the wire allows the current to pass. Right, that's the essential idea in here. So as a result, I'm also going to do it for the other capacitor, which is also, for this capacitor too. So I'm going to replace this thing with a wire. Let me connect this with a wire. So as a result, in that case, it's just a circuit like that, right? It's just a ohmic circuit. There are just resistors in here. What I notice is that this part of the connection from this point to that point is just connected by wires with zero resistance, which are connected with resistors with finite resistance. But you can see that the equivalent resistance between this point in here and that point is equal to 0. So it is quite easy to see that the current follows over the path that I have just traced out. So as a result, this current is going to go from here, continue like that, and continue like this, and to that point, and it will continue like that. Okay. So as a result, this is also equal to the current on the EMF device. Especially there are no currents, zero currents passing over the resistors represented by 1 and 2. Okay, so therefore, if I write down the circuit equation, That's basically the loop rule. I just go over a loop, doesn't matter which loop it is. So EMF is equal to I times R3. R3 is 3 ohms, so therefore current in that case is equal to 2 amperes. Okay, so this is what happens at time t equals 0. Okay, this is an artificial problem, of course. We know that all wires have some kind of a resistance, but we are essentially neglecting the resistances which are connected, associated with the capacitors. So with this assumption, of course, this is the solution. Right, so now let's look at what happens at t equals infinity. So at t equals infinity, the capacitors is full. Full means, let me just say it like this, charge does not change anymore. Does not change anymore. Whatever the charge variable is, this means that the rate of change of that charge variable is equal to 0. But we have physically connected this thing, mathematically connected this thing to the derivative of the, we have connected the derivative of the charge on a plate with a current that's flowing through that plate. So therefore, the current on that plate on the branch where the capacitors are equal to 0. So that's essentially the physical idea. When the capacitor is completely full, when the charge on them do not change anymore, in that case, we say that the current that flows through the capacitors is always equal to 0. So currents that flow to caps are 0. So that's the physical conclusion that we draw from this. So as a result, there won't be any current on that branch. Mathematically, this is equivalent to an open circuit situation. So what I would do in that case is to basically remove this, remove this capacitor in here, and these wires as well. So as a result, this circuit has the same solution as the circuit where there's a capacitor connected in that region in here, right? When there's a capacitor in here, I'm going to get the same solution as this circuit, okay? Because there's no current that's passing from here. So let's do it like that. So I'm also going to remove the capacitor in here. So this circuit has the same solution. So let's then look at the solution in here. There's a current that's flowing in here. Let me also call this as I. So this current is going to flow like that and then flow over this resistor and then go like this and go like that and of course continue like that, right? So in that case, the current is going to follow a different path. Of course, it's going to pass over all of the resistors. So in that case, if I write down the loop rule, this is I times R1 plus R2 plus R3. So in that case, the current is 1 amperes for these given values. Now, that's the solution for the currents. And let's then go back to our original circuit again. Let me place the capacitors once more. So there are these capacitors in here. There are no currents flowing over them, but they are still there. So as a result, I need to compute. Let me use a different color now. Let me use this strange color in here. So there's this point in here, A, and that point in here, B. So I need to compute the potential drop on AB. So for this purpose, let me erase. I think I'm going to erase everything. I know the capacitance values. And I can remember all the values. They are not that important anyway. So to find the capacitance, to find the charge on the place of the first capacitor, this one, let me call this C1, this is C2, I need to know the potential difference VAB. But I can find this potential difference when I go over this resistor. I basically follow this path. So in that case, this is equal to the potential drop on the resistor R1. So let me show it like that. So therefore, this is I times R1. So in this case, this is 1 amperes, 1 ohms. So that's a 1 volt potential difference. So that's VAB. And so therefore, the charge on the first capacitor is capacitance times VAB. So therefore, this is 1 microcoulomb. Okay. I then continue with the second capacitor. So this time the points that I need to consider are these. Let me call this as C and D. I need to compute VCD potential difference. This is the same thing as the potential drop on R2. So therefore this is I times R2. So in that case this is 2 volts because R2 is 2 ohms. So therefore the charge on the on the place of this, on the upper plate of the second capacitor is C2 times VCD. And again, it's 1 microfarad, but this time the potential difference is 2 volts. So therefore, this is 2 microcoulombs. Okay, let's just, let me show with color the signs of the charges. So upper plates are positively charged and the lower place should be negatively charged. So 1 microcoulomb is on that upper plate in here, and minus 1 microcoulomb is in the lower plate. For the other capacitor, for this one, again, the upper plate is positively charged. Let me put a little bit more charges in here because it's plus 2 microcoulomb on the upper plate and minus 2 microcoulomb on the lower plate. So we can also determine where the charges are.